Hey everyone! So today I'll be talking about space-optimal vertex cover in dynamic streams. This is joint work with Kiran Naidu at University of Bristol. Alright, so let's get started with the introduction of the problem. So what is the vertex cover problem, right? So given a graph, the vertex cover is just a bunch of vertices, such that if you look at any edge, one of its endpoints is in the vertex cover, right? So for example, for this graph, these three vertices form a vertex cover, because it covers all the edges, right? And the minimum vertex cover problem is like, what is the vertex cover of the smallest size? So for this problem, this graph, these two vertices form the minimum vertex cover. Great. So now, how hard is this problem to solve, right? So we know that in the classical setting, this problem is NP complete. But if you want an approximation, you can do it in polynomial time, right? So using this greedy matching algorithm, you can get a 2 approximation in polynomial time and even linear time. And when I say a 2 approximate vertex cover, it still has to be a vertex cover. That means it has to cover all the edges, but it can have twice as many as the optimal number of vertices, right? So if the optimal vertex cover has opt vertices, this can use 2 times opt vertices. All right. So the classical setting has this assumption where you can access the data at random, right? So you have random access to the whole graph, for example. But this might be infeasible when the graphs are very massive. So we deal with this problem in the streaming setting, where the information comes to you bit by bit, and the streaming algorithm looks at the current bit and updates the memory. And once that bit goes ahead, you've completely forgotten it. All right. So for graph streaming, the vertices of the graphs are fixed from 1 to n, but the edges appear in a stream, right? And instead of a bit, it'll be one edge appearing at a time. Great. So a trivial solution is always to store the entire stream, right? Store all edges. But that takes n squared space in the worst case, because if the graph is super dense, you have to store all the edges. So now the goal of this setting is to minimize the amount of memory. So first you want to maybe get a little of n squared space solution, which beats this bound, and then maybe try to minimize memory, right? All right. So let's talk about the different models, which are insertion only and dynamic. So in the insertion only model, edges can only be added, right? So let's look at an example here where these are the vertices and the edges come one by one. And this is the final graph, right? So this is the stream you see. And now we know that the problem is hard if you want to solve it exactly. So an exact solution requires n squared space, but the same greedy idea, it works in streaming and it gives you a 2 approximation. So this is insertion only streams, but what if edges could also be deleted, right? So that's where dynamic streaming comes in, and edges can be inserted or deleted here. So if you look at an example, these edges are inserted, and now you see this red edge, that's an edge deletion. So E1 was inserted and now it's deleted. And then you have some more insertions and deletions. And over here you can see that E1 that was actually deleted can be inserted back again. So this could happen even multiple times. All right. So this is the final graph, and you want to solve the problem on this final graph, right? So in our case, it's vertex cover. And a constant approximation needs n squared space. So this lower bound holds here still, but even a constant approximation needs n squared space in this model. And so, okay, what is the next step? You can think of an alpha approximation, right? Where alpha can be anything between 1 and n. And Dark and Conrad 20 gave a lower bound of n square over alpha square bits for this problem, and an upper bound of n square over alpha square times log alpha bits, right? So you can see that there's a gap of log alpha between the upper and the lower bound. And such gaps of polylog n appear very frequently in the dynamic streaming literature or even insertion only streams. And one main reason is counters or edges, like storing counters or edges need these log factors. So Sun and Woodruff in 2015 showed that for many problems, the lower bounds can be improved to include these log factors, right? So for many insertion only problems, they showed that the lower bounds actually include these log factors, and some like bipartiteness, approximate minimum cut. These are some examples of the problems they looked at. And Nelson and Yu in 2019 gave a lower bound for connectivity of n log cube n bits in dynamic streams. And you also know that there is an upper bound of n log cube n bits, making these log factors necessary, right? So Asadi Shah 22 was the first result that showed that these polylog factors can actually be removed in the upper bound. Like, it's not necessary to have in the upper bound. And they gave an algorithm for approximate matching using n square over alpha cube bits. And the lower bound was also n square over alpha cube bits. So this motivates our result, and we do a similar thing for vertex cover. So we give a randomized dynamic streaming algorithm that solves alpha approximate minimum vertex cover with high probability and uses n square over alpha square bits of space, right? And alpha can be anything less than n to the 1 minus delta, where delta is some small constant that you can choose. And this work closes the gap up to constant factors, right? So now we know that n square over alpha square is the right answer for this problem. Great. So now let's talk a little bit about our algorithm. And we will start with the dark Conrad 20 algorithm that will be like helpful to understand what our algorithm is. And one simplifying assumption I want to make here is that the input graph is bipartite, but this can be easily lifted, right? Okay, so let's talk about this algorithm. What do? They first partition the vertices into groups of size alpha, right? So there are roughly n over alpha groups. And now they look at a pair of groups and store a counter between them. So for every pair of groups, there's a counter, and the counter stores the number of edges between those two pairs of groups. So you store it for all pairs, like all of these, right? And each counter storing the number of edges between the pair of groups. All right. So this is what you do when the stream comes, but after the stream, you construct a group level graph. And what I mean by that is look at two groups, and if there is an edge between them, let's say for example this one, if the counter is greater than 0, you put an edge between them. And if the counter is equal to 0, then you don't put an edge between them, right? And now you find the vertex cover of this graph, right? So you think of a group as a single node and you compute the vertex cover of this graph. And then to give an alpha approximation to the vertex cover of the original problem, you output all of these groups that you selected in the group level vertex cover. So why is this an alpha approximation? So if you look at this is clearly a vertex cover because for any edge, you picked an entire group endpoint as in the vertex cover, right? So it is clearly a vertex cover, and it's an alpha approximation because instead of picking one vertex, you picked alpha vertices. And so it's an alpha approximation. Great. So now let's look at how much space this uses. So the counters each use log alpha bits of space. Because if you look at a pair of groups, there are alpha vertices here, alpha vertices here. So there are at most alpha square edges. And this means you need a counter of log alpha bits. And so you do this for all pairs, there are n square over alpha square pairs. And so that this total space needed is n square over alpha square times log alpha bits. And this is the issue here. This log alpha is what we want to get rid of, right? So what is the issue? That these pair of groups have a lot of edges between them. And so we need to use counters that count up to alpha square edges. And the goal is to get this to constant number of edges. So counters can use just use constantly many bits, right? So let's first solve this problem for sparse graphs. So a sparse graph is any graph. I'm defining it as it has less than equal to n square over alpha square edges, right? So now for such a graph, if you randomly partition this into groups of size alpha instead of arbitrary partitioning like we saw earlier, now if you look at any pair of groups, there are at most constantly many edges between them in expectation, right? Because there are n square alpha square edges and the same number of pairs of groups. So any pair of groups will have just a constant number of edges between them. And so I just need to store a counter that counts up to some constant, which takes constantly many bits. But as soon as this goes slightly above, so the number of edges increases by a small factor, so it's n square over alpha to the 1.99. Now these pairs of groups have alpha raised to 0.01 edges between them, and I again need log alpha bits And this is a problem, right? So we've solved the problem for sparse graphs, but as soon as the graph gets slightly dense, we run into this issue again. So now the question is, how do you solve this issue in general? Because G may not be sparse, right? And now we have this lemma that comes to save us. We call it the match or sparsify lemma. So this lemma gives us a matching M such that either M is very large, it has a size of at least n over alpha. And if this matching has a size of at least n over alpha, that means the vertex cover of this entire graph also has to have size at least n over alpha. Why? Because at the very least you need to cover all of these edges, and so one of their endpoints should be in the vertex cover. So you have size at least n over alpha. And as soon as opt has size n over alpha, the whole vertex set V is an alpha approximation, because this is of size n and this is of size at least n over alpha. Alright, so we're done in this case. So if the matching output by this lemma is large, we're done. So what if it is not large? So the other case is that if the matching is not large, then the residual graph will be sparse. So if this matching is not large, as you think of it is deleting all of these vertices, and now the residual graph is very sparse. Okay, great. So now we've already seen how to solve this case, right? You use counters that count up to some constant and that uses constantly many bits in expectation. So we're done, right? And this is our entire algorithm. We randomly partition the vertices into these groups of size alpha. Then we run match or sparsify. If the matching output is large, then we just return V as the solution. Otherwise, we look at the sparse graph and run the algorithm for the sparse case, which is compute a group level vertex cover. And now finally, you want to output this group level vertex cover, but you also have to cover these edges. So you output all the groups the matching is a part of, right? So if a vertex lies in a group that is part of the matching, then you output that. And this won't destroy our approximation because the matching size is small. So this together gives you an alpha approximation. And so we're done. Now the only thing left to prove is this match or sparsify lemma, right? How do we prove this lemma? Great. So now let's go to the match or sparsify lemma, which we call the key lemma. And this is what we need to show. That in n square over alpha square bits of space, we either get a large matching or a sparse residual graph. So let's try uniform sampling as our first approach. So you sample a bunch of edges uniformly at random, and this is n square over alpha square times maybe some polylog in the denominator, so that you use just n square over alpha square bits of space. And then you use M to be a greedy matching over all the sampled edges, right? So sample a bunch of edges at random uniformly, and then M is just a greedy matching over them. And this clearly uses n square over alpha square bits of space because sampling an edge takes polylog n space in dynamic streams. Great. So now the residual graph is sparse if you do this. And what we can prove is that the residual graph has a maximum degree bound of roughly alpha square. Okay, so let's see why this is true. So if you think of any vertex that survives with at least alpha square neighbors, we'll show that such an event happens with a very low probability, right? That if a vertex U and a lot of its neighbors survive, that is very unlikely. Okay, so firstly, none of these edges should be sampled. Why? Because if this edge is sampled, and if it is included in the matching, then both of these endpoints don't survive. But if it's not included in the matching, then either this endpoint doesn't survive, is deleted, which means U is not in the residual graph, or this is not in the residual graph, which means U's degree will decrease in the residual graph. So we don't want any of those, so none of these edges should be sampled. Okay, so there are roughly alpha square of these edges, n square edges in total. So the probability that you don't sample anything from here is 1 minus alpha square over n square. But you're repeating this process multiple times, you're doing it roughly n square over alpha square times. And so this is the probability that U survives along with a lot of its neighbors. And this happens with very low probability, which is 1 over poly n, right? So now basically we can say that if U survives, it can't have more than alpha square edges, roughly. And so we get a max degree bound. Great. But this is not solving the entire problem, because this only works for small alpha. And this is because the sparse graph we want has to have n square over alpha square edges, not more. But the max degree bound we get is alpha square, right? So if all the vertices have roughly alpha square edges, then we want this to be less than n square over alpha square, then alpha has to be less than n to the 1 over 4, right? Because the n's cancel and this becomes alpha 4. Great. So this works for small alpha, but we still have to solve the problem for large alpha. So to do that, let's understand what exactly the issues are, what exactly the drawbacks are with this, right? And the first drawback is that you don't need a sparse graph when you find a large matching. So this algorithm is something like match and sparsify, because you always get a matching and you always get a max degree bound. But you don't need the max degree bound in this case when you get a large matching. So the fix one is to do the analysis slightly differently and do it in terms of match or sparsify. So when you get a large matching, you don't need a sparse graph. The second drawback is that there is a hard instance showing that uniform sampling does not work for large alpha. And roughly the intuition is that uniform sampling is kind of biased towards these high degree vertices, right? And this itself wouldn't solve the problem. So this drawback is needed, and you need to fix it using non-uniform sampling. Great. So now in this attempt, we address both the drawbacks, and just doing these two things gives us the lemma we want. And so match or sparsify is proved, and we're done. Great. So now there's this small thing I want to talk about, which is the space, right? So note that we're completely done with the algorithm, but something weird is happening with the space. If alpha is super large, is n to the 1 minus delta, then the space used is just n to the 2 delta bits. And if you think of delta as some small constant like 0.1, this is like n to the 0.2 bits. But how do you even output the vertex cover, right, in just n to the 0.2 bits, because the vertex cover could be of size omega n. Just writing down the vertex cover will take more space than you have available. So what are you going to do? So we output a very structured solution, right? So you recall that we either output an entire group or no vertex from the group. And so we can just output the group numbers, the group indices, right? And this takes just O tilde 1 space. And this means the space is n over alpha, because these are the number of groups, times O tilde 1, which is O of n square over alpha square bits, right? And the groups themselves don't take a lot of space because we don't do grouping completely randomly. We do it using hash functions, and that also takes small space. So basically we're done in n square over alpha square bits of space. Great. So now let's conclude. We give a match or sparsify lemma, which in n square over alpha square bits of space either gives you a large matching, which implies a large vertex cover, and so you're done because you can output the vertex set V as the solution, or you get a sparse graph. And how do you solve this case? You use ideas from Dark-Conrad 20 along with random partitioning. And you can again solve this in n square alpha square bits of space. And note that we run both of these algorithms in parallel during the stream. So you only think of it one after the other, like running this and this, which is in post-processing. But during the stream, they run together and we get the final algorithm. So this gives us a dynamic streaming algorithm that with high probability gives you an alpha approximation to the minimum vertex cover and uses n square over alpha square bits of space. Now Dark-Conrad 20 gave a lower bound of n square over alpha square bits. So this makes our algorithm optimal. And this also shows that these polylog n overheads are not always necessary, like Asadi-Shah 22. So now let's go to some open problems. Could similar techniques to this work in Asadi-Shah 22 be used to bypass these polylog n overheads for some problems? And some problems we have in mind are like dominating set or spectral spacification. And also another problem which is closely related to this one is that how well do deterministic algorithms do, right? So you use n square or alpha square bits of space and solve the problem, or you improve the lower bound. So which one of these cases is true for deterministic algorithms? And the current best deterministic algorithm is that of Dark-Conrad 20, and it uses these n square of alpha square times log alpha bits of space, right? So there is a log alpha gap in this understanding, and we want to know what the right answer is. Great. So I leave you with these two open problems, and thank you so much for listening.